What we're talking about today, this is lecture 8. And I'll start out on video, but it turns out, as I mentioned to a couple of you, the video data sets are just too big and they take forever to load. So this is going to be just one short thing. Then I'm going to follow this with just still images of structures I've drawn and voiceover. I'm going to try to save data that way and make it more possible for my processor, my producer here, to get them up to YouTube. So here we go. So this subject is chapter 7 in Smith, called Alkyl Halides. And the alkyl halides are any compound where a halogen has replaced a hydrogen. And I want to make clear to you the significance of this. So the first thing is the structures. It's any compound of this sort where one of the hydrogens bound to a carbon is replaced by a halogen bonded to the carbon, fluorine, chlorine, bromine, or iodine. And that's a huge difference. I'll explain why in a second. But compounds of this kind, now you would know to call that 2-fluorobutane. But the real significance is the replacing a CH bond by a CF bond. And the significance, it's really, it's made numerical by Linus Pauling's table of electronegativities. The table of electronegativity, the notion of electronegativity, is an invention of Linus Pauling, I think in the 1930s. And he just assigned values of the tendency, that describe the tendency of a nucleus to attract electrons in a bond towards it, and rank them. And here are the values. Fluorine is the highest with 4.0, and down here in the lower left of the table with potassium at 0.8. So the whole range goes roughly from 0 to 4. And then part of the second period, the atoms we care about, boron's 1.8, carbon 2.5, nitrogen 3.0, oxygen 3.4, fluorine 4.0. And let's just look also at the other halogens. The halogen, of course, of this group at the right of this table, 4 for fluorine, chlorine's 3.2, bromine's 2.7. Okay, so that's really the matter. Now, let's just limit this. Let's limit this table to the compounds, to the atoms that form bonds that we care about. We're not going to do much with boron. And for the present, we're not going to worry much about even the third period here. We're going to consider just bonds between these atoms. And the important thing here, I can represent with some arrows. So I've done a little bit of editing on this table, or a lot of editing. And what I have now is a difference in electronegativity, carbon to the other atom. So in the case of a carbon to hydrogen bond, the electronegativity of carbon is 2.5, the hydrogen is 2.2. 2.5 minus 2.2 is 0.3. So if we represented 0.3 by an arrow, let me just say, since the carbon has a higher value than the hydrogen, it's a well, let's make it a short arrow going up. Now, in contrast, the carbon to fluorine bond has electronegativity difference of 2.5 minus 4, so it's minus 1.5. The electrons in the bond are drawn more to the fluorine. They're drawn in this way, and that's 5 times as long. So I want to make an arrow that's about 5 times as big, and in the opposite direction to that of a CH bond. Even longer, 5 times as long. And that's the difference. That's a huge difference. The electronegativity is large and it's directed towards the halogen. Now, the C to carbon to chlorine bond is a difference of 2.5 minus 3.2, which is minus 0.8. So it's again in the direction towards the halogen and about half as strong, a bit more than half as strong as the carbon to fluorine bond is. And finally, in this little table, the carbon to bromine bond has electronegativity difference of minus 0.2. So again, it's a little short arrow, but again, it's pointing towards the halogen. And this difference, this is the whole story. This is the whole point. This is the whole interest, reactivity of the alkyl halides. There's electronegativity difference that, in the case of the halogens, sucks electron density of the shared pair away from the carbon. And there's another, I can use another color to represent the effect here. Because the electrons are being pulled away from the carbon towards the halogen, we use this symbol. This is a delta, Greek letter delta, positive. That symbol means the carbon in the alkyl fluoride, this is a 2-fluorobutane, the carbon has a small positive character. The effect of a halogen bonded to a carbon is often represented by this delta positive. And what that implies is that the carbon has some positive character. It's in some way hungry for electrons. In some way it feels that it doesn't have all the electrons it should have. That is characteristic of each of these. The delta positive value in the carbon fluorine is the strongest, but there's partial positive character to each of these carbons. And another way the other effect of this, the same effect is described as a polarity. We say that's a polar bond, meaning that the electrons that glue together the carbon and the fluorine are pulled more towards the fluorine, leaving the carbon somewhat electron naked. That's also true of the carbon chlorine and with the carbon bromine bond. And that effect, that polarity of the bond is the whole story. It makes, now let me just not stop again, but just let's get rid of this information for now. What we want to say now, and I'll show this in fixed images that will follow this introduction, but we consider now a new idea called a nucleophile. I shall explain this at a little more length, but this is an important word. In fact, I think it's the single most important word in organic chemistry. And when you master this notion of something being electrophile, a lot of doors will open for you in organic chemistry. So get it, don't resist it. A nucleophile is always referring to a chemical species. And a nucleophile always has this character, these properties. A nucleophile will always have a pair of electrons that it's available, that can be shared. And so it has an unshared pair of electrons, and it can use that electron pair to form a bond to a carbon if it finds a carbon that is willing to accept a pair of electrons. So in this case, I will use a symbol that is pretty common in this practice of organic chemistry. Nu with a pair of electrons, and the nucleophile, the chemical species, often has a negative charge. It doesn't have to have a negative charge, but it often does. So in a reaction that I will represent now, in a live action, and then describe some more because it's so central and so important. I really want you to get this. A nucleophile can take its pair of electrons and we say attack that carbon and kick that fluorine out. Those two curved arrows represent the migration of a curved electron. This is the big deal here. An alkyl halide is vulnerable, or many alkyl halide compounds, the carbons bonded to halogens are vulnerable to a nucleophilic attack. This is the language that organic chemists use, an attack, as if it's a war game. And the effect of such an action will be that the carbon framework will remain, so a 4-carbon chain, 1, 2, 3, 4, and now there is a new bond between the nucleophile, to carbon. That black line is a new chemical bond. Not drawn the way we usually draw them, but you can deal with that. And the fluorine in this case is separated from the carbon, and it has left with a negative charge. It took its unrepresented, unshared pairs, 2 there, 2 there, 2 there. It shared a pair with the carbon, but it took both of those in this action. It took both of those electrons. So fluorine is leaving with an octet of electrons around it, and that gives the fluorine a negative charge. That reaction, as represented there, is called a nucleophilic substitution reaction. A nucleophile has substituted for fluorine in this action. The action is represented by those curved arrows, and the result is a perfectly fine alkyl halide is turned into an alkyl nucleophile, whatever nucleophile is. I shall pick this up in fixed images. Thanks.